So be aware of that. In our course, that complication will not be there, and therefore whenever you're taking a derivative of a vector, you have to get a vector. But more importantly, you should avoid the kind of mistakes I'm doing over here in some of the things I'm writing over here. For example, I should have put the frame of reference over here, okay, as a pre-superscript. So before the D, I have to put a superscript saying it is with respect to a particular frame of reference. Could be A, could be E, which is the Earth. A could be the aircraft fixed frame, or it could be I, some inertial frame of reference. Let's say star fixed is the closest we can get to an inertial frame of reference for most things that we observe on Earth, because the star system, the constellations, are reasonably constant. They, compared to even a sun fixed system or a Earth fixed system, star fixed system is probably the best that we can get to in terms of an inertial frame of reference, because that's not accelerating as much, or the relative accelerations are not going to change your derivations too much. Okay, so now it's the same thing, exact thing that we were talking about F. Now I just replaced it V. So wherever there was F1 and F2, now we have V1 and V2. So now I have a vector which is a sum of two vectors, and therefore I can take the derivative of the sum as the sum of the derivatives. Okay, so that's exact same extension or extrapolation of what we know from scalars. We are extrapolating it to vectors. Now coming to one more slightly different example than what we had there, because with scalars the product was very simple. There's only one way of defining the product. Here we define it as dot product and cross product, or the vectors product with a scalar. Okay, so there are like at least three different ways in which the products with having vectors as one of the components in them might be related. If both the components are vectors, then it could be a dot product which leads to a scalar quantity like f of t, v1 dot v2. On the other hand, if it's a cross product, it remains a vector, and which is why of course you call the dot product as a scalar product of two vectors, and the cross product is called as a vector product of two vectors, because after the product is taken, it remains a vector, whereas here it gets converted to a one order lower tensor from a first order tensors that you have, which are vectors, to a zeroth order tensor, which is a scalar. So that reduction is what your dot product does, and this is at two first orders becoming zero. So similarly, you could have two second order tensors which will become just a second order tensor, depending upon how many times you have the dot, and so on and so forth, right? So you could have a single dot or a double dot. If you have a double dot contraction of two second order tensors which are dyadics, then you end up with a scalar and things like that. Again, these are things for your future. In the undergrad courses itself, you will see some of these things, but in this particular course you will not see those things, which is why I have not explicitly written it out, but I'm just talking about it as further extrapolation. We are already extrapolating from scalar to vector. Things seem so simple. Extrapolating from scalar vector to dyadic, and then the quartic, which is the fourth order tensor, etc., are exact straightforward things. But if you directly try to study them, then you think it's overly complicated, something that is very difficult. The learning curve is very steep, and all these kinds of cliched statements that you come up with. But in reality, you see that if you take it in a step-by-step approach, what you understand, what you know, to the next level of what you do not know, and then gradually go up there, climb the mountain like that, then the mountain climb is not so tiring for you, right? So coming to the first one, the product with a scalar. So once again, it's a derivative of one multiplied by the other as it is. So in this case, the scalar remains the same, then the vector's derivative, the scalar's derivative, and then the vector remains the same. So it doesn't matter what two you're multiplying and how you're multiplying, you have to retain that. So if it's a dot, you retain it as a dot. If it's a cross, you retain it as a cross. That's all that you need to remember. So in this case, you have a dot product, and therefore it becomes take derivative one at a time, keep the other the same, but you keep that. And again, this is also commutative, so it doesn't matter if you interchange, but here it does matter if you interchange, it will become the negative of that. So therefore here you have to be a little careful about the ordering of that. You retain the same order as what you started off with. So you see the ones are always first in both the terms, and the twos are always later as you see over here, because that's how the function v of t is defined. So I think these are some of the things that will be required for your first homework, which is due next Thursday, or rather second homework, which is due next Thursday. So you can always go back to the slides to look it up if you need to, but I'm sure most of these would have become muscle memory because of your linear algebra course, etc. Right? So we'll often use these relations during our derivations. We may not be explicitly stating that this is that particular rule, but many a times we'll be utilizing that. But in your homeworks, when you're presenting, I would like you to specify that particular rule so that you know what you're taking advantage of. Even though it might seem like obvious, stating that out many a times helps you ingrain that in your muscle memory if you have not yet done that, right? So then it becomes much easier when you go forward to more and more complex problems that we'll be dealing with later on towards the second half or close to the end of this course, when rotations, especially in 3D, would have been introduced. Okay, the first two for calculation, why those are very important, especially the first two, is because you see over here. Oops, I think I have the same slide. Yeah, I think I have the same slide. Yeah. So then the vector functions derivatives. So if you look at, I think we covered and I erased that. We said that when actually, I think in answering Gracie's question, I was talking about the distinction between measure numbers on the one hand and the components and or the ijk unit vectors on the other hand. So here I think it will be a little more clearer because the vector typically is represented in terms of its measure numbers. So when I'm talking of measure numbers of v, then I'm talking of vx, vy and vz, and I could probably put them in a column matrix. But if I do that, I have to very clearly specify that it is for the ijk system, because if it's for some I star, j star, k star, it will be an entirely different set of numbers, vx star, vy star and vz star. So keep that always in mind. But in this pristine form that it is written over here, it doesn't need any unit vector as it is, but it's something that is hypothetical in a mathematical sense, but you cannot actually do a numerical implementation of that as it is. If you want to do a numerical implementation, you have to bring in unit vectors, and once you define those unit vectors, you have a particular set of the measure numbers. The measure numbers could be actual numbers or it could be functions, but essentially they are scalar quantities. Okay, that's all that you have to remember. So again, when you're taking the derivatives of such vector functions like v, you need at least these three important things. Remember that I have to, if I take derivative of v, I have to say v dot with respect to which frame. Okay, so I have to prefix this with an a, e, I, etc. Which frame I'm taking, aircraft fixed, earth fixed, or an inertial frame of reference. Sometimes the aircraft fixed, if its aircraft is just cruising, might be considered to be an reasonably good inertial frame. Earth many a times is considered to be a reasonably good inertial frame unless you're doing some kind of a spacecraft dynamics problem, etc. Right? There might be certain wrong practices that I have in the slides. Don't take over that for your homeworks and things like that. So because I'm very clearly mentioning what is missing. Okay, so I should have put a superscript, pre-superscript over there, right? So once again here it's using some of those rules that we just saw. Because v is defined in this particular way as a sum of three things. Instead of taking the derivative of v, I can take the sum of those derivatives. Instead of the derivative of the sum, I can take the sum of the derivatives. So I take derivative of just the first term alone, second term alone, third term alone, and then add them up. Okay, and then within each one of them, it's a product rule that is getting applied. Okay, because each of them is a product of two quantities. So I take the derivative of one and then keep the other as it is. I take the derivative of the second and then pre-multiply it with the other thing as it is, right? Which is what is an expanded form out here. You see that first term is over here and here, which is essentially you're talking about taking the derivative of not only the measure numbers but also the unit vectors, okay, because the unit vectors could probably change in time. For example, this IJK might be an aircraft fixed frame, and the aircraft itself is performing certain maneuvers, and we are studying, let's say, a particular rudder deflection, for example. So now we want to study the rudder deflection with respect to the aircraft fixed frame. The aircraft's IJK, it's also moving with respect to the earth fixed frame. So in the inertial frame of reference, you need these I dots, J dots and K dot terms as well. You cannot do away with that, okay? So whether this term will be non-zero or just trivially go to zero, of course, there are certain questions that is asked over here. Can these unit vectors change? Do we really need this I dot, J dot and K dot? So, which is why you have to mention the frame of reference. Right now I was talking about a frame of reference which is aircraft fixed. Then you might, the answer to this might be one level, yes or no, okay? But if it is instead of the aircraft fixed frame, I'm talking about an earth fixed frame, the answer might change. An yes might become a no, or a no might become an yes. So you have to be aware of that, which is why so much of an importance for specifying as a pre-superscript here which frame you're taking the derivative with respect to, okay? So one is the importance of the frame of reference, which is what we said, one of the requirements. The other is the coordinate system, okay, which coordinate system you're taking, because that XYZ that we introduced, your unit vectors are going to be tangential to that, and therefore that choice of the coordinate system becomes important. So, and again, within the coordinate system, whether it's a Cartesian coordinate system or a polar coordinate system or a cylindrical coordinate system, spherical coordinate system, or any arbitrary curvilinear coordinate systems like we saw, it could be orthogonal, need not be orthogonal. Most cases will be taking a Cartesian coordinate frame, which is a dextral triad. What do we mean by dextral? Dextral means right-handed. So dextral triad means that if I take the cross product of B1 and B2, I should end up with a B3, okay? So that's essentially your right-hand thumb rule that you're going with, right? Now, that is very, very critical. In fact, I remember in one of the courses that Professor Hodges was teaching, even though it was an advanced dynamics course for the master's level and some PhD students as well. In the exam, everybody was trying to calculate, and then they were trying to do this. And there was this one guy who had probably not studied much of the notes, and he called Professor Hodges and asked, why is everybody doing this? Then he said, you have no place to be in this course, because it's that important, because the sign changes, and if sign changes in between, and many of these are algebraic sums, you might not just end up with the final result sign change alone, but the total answer itself might completely change. So it's very, very critical, so that once you fix a particular system, you stay with it. It's not necessary to use a dextral triad. You can use B1 cross B2 as minus B3, which is a left-handed system, but you have to be consistent throughout your derivation with that, okay? Then you'll end up with the same inference about the motion as you would with a right-handed rule, just that because we're all doing similar problems, it helps to have a convention. Otherwise, every time we have to explain, no, he used a dextral triad, he used a left-handed system, and therefore this intermediate result is changing. So that explanation can be precluded, avoided, if you can all follow the same convention, okay? And again, of course, it's not necessary. One is dextral and left-handed. The other is not necessary, as we already saw, that these be at right angles. So they can be at any arbitrary angle as long as they are not coplanar and collinear. The other thing is they need not even be straight lines. They could be curved lines, as we already saw. So curvilinear coordinates, which are changing along the length. But those are useful for certain more complex problems, most of which you will not encounter in this course. So, but just to be aware of all these possibilities, just that be consistent. You use a coordinate system which helps you solve the problem in the most efficient manner, which is why the choice of these three for each and every problem becomes so very critical. First, choose your reference frame, and at least one, and many problems more than one. Okay, then you choose for that reference frame what are the unit vectors that you're going to use, and then the appropriate coordinate systems. It's usually the coordinate system first, and then the unit vector, because the unit vector is defined as a unit tangent to the coordinate curves. So once you have the curve x, curve y, curve z, then ijk get automatically defined. Their magnitudes anyway are known. It's because it's unit vector. Now they're defined as tangents to those three curves. Okay, so always in this particular order. It's not just these three, but also in this particular order that you have to introduce these things to make your solution process very effective. Then can unit vectors change? And because they do change in general, that's why you need the frame of reference and its specification, and therefore the coordinate system as well. Then the inertial frame of reference, which is under which Newton's laws are valid, and we already said that that is a mind game because there's no such thing in reality, but it's the relative motions that we are interested in, and therefore we will assume for all practical purposes, for all engineering purposes, that we are dealing with inertial frames of reference, and that we are introducing Cartesian coordinates, which are the easiest to differentiate. But in this course itself, we will also go beyond Cartesian coordinates to polar coordinates, and in 3 dimensions to the cylindrical coordinates, to show you the utility of those for specific kinds of problems. Then non-inertial frames of reference and or non-Cartesian coordinate systems, as I already mentioned, are useful for certain courses which you will not encounter in this particular course, but they definitely make things life much easier, because if you are trying, because you know only Cartesian coordinate system, you know only about laws in the inertial frame of reference, you try to force yourself for a complicated problem to try to do with this, it's going to even more further complicate the solution process. You might as well learn a little about this and then implement it. Okay, so overall, though of course in these cases the differentiation becomes a little more difficult, because for example in the Cartesian coordinate system everything is hunky-dory. You have those bi dot to bj is the Kronecker delta, your bi cross bj can again be found through a permutation tensor. Then again you know that throughout the x curve the I is going to be the same tangent, it's not going to change directions because this is a straight line. J is going to remain the same, k is going to remain the same. So you see that these are the things that will make simpler problems more amenable to this particular choice, depending on the geometries involved and the way in which the motion itself takes place. This might become more useful at some other time. So I'm sorry I overran, but I just wanted to complete this particular slide. And so we'll meet on Monday, and you'll present the hare and the tortoise. Looking forward to it. Thank you.